Hello folks, this is question 1 from tutorial 6 and we're talking about introducing habitat value into a forestry model. So what are we talking about? We've got a graph here and there seems to be a lot going on, but it's quite simple. We've got a graph here. Dollars over time. And this refers to the optimal rotation of a forest. That is, after how much time or what age of the trees should we optimally cut them down, harvest them, sell them for wood and replant them? Well, we can make that decision based upon the marginal benefits of waiting one more year and the marginal cost of waiting one more year. These two marginal values represented by this curve here for marginal cost and this lower of the two curves here for marginal benefit. We're going to shift this curve in a moment, and that's why the second curve's there. But for now, just pretend the second curve isn't there. So marginal cost of waiting 1 year versus marginal benefit, the lower of these two curves. Now, like a lot of things in this subject, we look for the equilibrium point. That is the point where marginal benefit equals marginal cost. That equilibrium point, drop down to the time axis, will tell us the optimal age of the trees when they should be cut down. Now let's look at the variables in both the marginal benefit and marginal cost sides. So marginal benefit, what benefit do you get for waiting one more year before you harvest your trees? Well, you get this delta V. That's the change in the value of the extra wood that's grown over that year that we waited. So there's extra biomass after one extra year, and that's the value of it. For the moment, just pretend this H doesn't exist. Just pretend on this left side of the equals, there's only delta V. We're going to introduce the H. So the marginal benefit of waiting 1 year is the extra value of the wood that's grown in that year. What are these variables over here for the marginal cost side? Well, we have the value of the stock of wood at the current period. We subtract from that the cost of harvesting. This R is the discount rate. And this S is the value of the land once the trees have been harvested. And then we have another discount rate here. This may not seem very intuitive, this form, but it's derived from a different form that's covered in the lecture. So, marginal benefit equals marginal cost. This is the time at which we should cut down our trees, as represented on this graph by the equilibrium. So now let's introduce this idea of habitat value. Instead of just talking about the benefit being of waiting before we harvest being the extra wood, surely there's some biodiversity value, some habitat value. In the textbook, it refers to the value for the habitat of a spotted owl, some rare creature. When we add this habitat value, we add it to the marginal benefit side because this is a benefit. The way we model this on our graph is shifting this marginal benefit curve from marginal benefit 1 out to the right to marginal benefit 2. So this curve is shifted because there is extra value in waiting one more year before we harvest. The consequences of that shift, an increase in time, which is really an increase in the age of the trees before we decide to harvest them. How do we know this? Well, we use the same rule as before. We looked for where MC equaled MB, and that gave us the time. But now with this new marginal benefit curve, we look at the new equilibrium, where they are now equal. And this has resulted in the time being greater. Or in other words, the trees are older when we harvest them. We've just looked at the way to calculate the optimal rotation of harvesting trees. We've done it in the context of a marginal benefit and a marginal cost, which we've graphed. We know that the marginal benefit without habitat included is merely the change in the value of the extra wood that's grown. But when we add the habitat value, which we literally add to this side, this has an effect of shifting that marginal benefit curve with a new equilibrium and a new age of trees when they should be harvested.